Every deck of cards comes off the assembly line looking like this: ace or king, suits in order. There are 52 factorial ways to arrange this deck of cards. That's 8 followed by 67 zeros. If every atom in the observable universe had been shuffling its own deck since the Big Bang, you still wouldn't have come across a perfectly sorted deck. And yet, you've never seen a shuffled deck sort itself. Nobody has. Order isn't forbidden. It's just that the odds are so weighted that forbidden and statistically impossible collapse to the same thing. This is what physicists call entropy. But if it's not forbidden, just really unlikely, then that's worth sitting with. Nothing in the laws of physics says the cards can't shuffle themselves into order. No force prevents it. Newton's laws work perfectly fine in reverse. At the microscopic level, there's no arrow pointing forward. Here's the thing though, the deck doesn't know if it's shuffled or not. Only you do. Disorder isn't a property of the cards, it's a property of your knowledge of them. Entropy is the gap between what you can see, a shuffled deck, and what you can't, the position of each card. So ask yourself, what if you could close that gap? What if you could see every card as it moves and sort as you go, recording the position of each card? That's exactly the same thought as a physicist named Maxwell had in 1867. In 1867, the physicist James Clerk Maxwell had a problem with this. Not with the second law itself, but with what people thought it meant. The second law says entropy always increases in an isolated system. When left alone, disorder only grows. Everyone treated this as an absolute, fundamental, as if it were carved into the universe itself. Maxwell thought it was just statistics, a consequence of our ignorance, and he wanted to prove it. So he imagined a box of gas divided by a wall, both sides at the same temperature. But at the molecular level, speeds vary. Some fast, some slow, all mixed together. Now, he placed a tiny, intelligent demon at a small door in the wall. The demon watches each molecule. Fast ones, he lets through to the left. Slow ones, he keeps on the right. No pushing, no forcing, just watching and choosing. One side gets hot, and the other gets cold. A temperature difference, created from nothing, from a uniform system, without doing any work. You could run a heat engine between those two sides and extract useful work forever. Maxwell's point was, the second law only holds because we can't see the individual molecules. A being who could wouldn't be bound by it. The law isn't about physics, it's about the limitations of what an observer can know. For 60 years, nobody could kill this argument. Then, in 1929, the physicist Leo Szilard decided the cost had to be hiding somewhere. He just had to look for it. So he asked a very precise question. What exactly is the demon doing step by step? To sort each molecule, the demon has to measure it, remember the result, and then act on it. For every molecule that passes through that door. Eventually, his memory fills up, one bit of information at a time. And here's the thing about memory. It's physical, whether it's a notepad, a neuron, or a semiconductor. A bit is always encoded in some physical form. In order to keep working, the demon has to erase. And in 1961, the physicist Rolf Landauer accidentally proved something extraordinary about the act of erasing memory. Erasing one single bit of information releases a minimum amount of heat. K is Boltzmann's constant, the bridge between temperature and molecular energy. T is temperature in Kelvin. The natural log of 2 comes from the binary choice. 2 possible states collapsed into one outcome. the information the demon erases about which side the molecule is on doesn't just vanish. It gets distributed into the random thermal motion of the environment. It becomes heat. The certainty he built up, left or right, gets unknown, and that unknowing has a price. The heat released by erasing is exactly enough to cancel the entropy the demon reduced by sorting in the first place. The second law survives. By exactly 1 bit's worth of accounting, the universe keeps perfect books. This isn't just a thought experiment that was solved and forgotten. It tells us something important about every computation that has ever happened. Every time a transistor resolves a logic gate, 2 possible inputs becoming 1 output, it erases uncertainty, and erasing uncertainty has a minimum cost. At room temperature, Landauer's limit is about 2.85 times 10 to the negative 21 joules per bit erased. That sounds negligible, but a modern CPU erases on the order of 10 to the 18 bits per second. Landauer's theoretical floor is about 3 milliwatts. Your CPU runs at about 10 to 100 watts. We are still 4 to 5 orders of magnitude above the Landauer limit. But that limit is real. It's a wall written in physics, not engineering, and we are heading towards it. Your computer isn't getting warm because of bad engineering. It's getting warm because it's forgetting, constantly, at a rate no amount of engineering can ever fully eliminate. Entropy isn't the universe losing energy. It's the universe losing information. Permanently. Irreversibly. The arrow of time isn't written in energy. It's written in what cannot be remembered.